Okay, so now we're in 4.8, and we're going to be looking at three important vector spaces that you can associate with any matrix. So to begin with, let's let A be this matrix here. And as we've already defined before, I'm going to consider the rows of matrix A to be row vectors, and the columns of of matrix A to be what we call column vectors. The row vectors, you'll notice, have n entries in them. So if A is an m by n matrix, then the rows will be vectors that live in Rn. The column vectors, you'll notice they each have m entries in them, so the columns live in Rm. So these are the three vector spaces that we associate with the rows and columns, and there's actually one more that's not explicitly related to those until we talk about some theorems, but three vector spaces that are associated with that matrix A up there. So the first is called the row space. The row space is the space that's spanned by the row vectors in A. And just a reminder, because this is an important theorem, when we first introduced the concept of span, we showed that if you take any set of vectors in a vector space and take the span of those vectors, remember that's the set of all linear combinations of these, then that span, that new set that you create that way, is automatically going to be a subspace. So if anytime we write span of some set of vectors, we know for sure it's a subspace. The column space is the subspace spanned by all of the column vectors of A. And then finally we have the null space, which if you set up this homogeneous linear system, AX equals 0, the solution space, you'll remember that the set of solutions to a homogeneous linear system is always a vector space. The solution space of this we call the null space of A. All right. Something worth pointing out here, the row space and the null space would both be subspaces of Rn. So if you remember just a second ago, we said all of the vectors in the row space, all of the rows of A are vectors in Rn. And so the span of those vectors would be a subspace of Rn. The null space is also a subspace of Rn because, again, the null space is the set of solutions to this equation. So the values of x that work in this equation make up the null space. And if A is an m by n matrix, then x has to be an n by 1 matrix, making those vectors vectors in Rn. The column space, we can see, would be a subspace of Rm instead. Okay, so there's this section is going to be kind of a lot of theorems relating these new vector spaces to each other in different ways, and also providing us with some insight into how they relate to solutions for linear systems. So first theorem we're going to talk about, if you have a linear system AX equals B, not homogeneous necessarily, just any linear system, then this linear system is consistent if and only if B, this B right here, is in the column space of A. Okay, so the column space of A can actually be thought of as the set of, it can be considered the set of all values or all vectors B that can be put here to give us a consistent system. So it's an if and only if proof. We have two directions to prove, but the two directions look essentially identical, just one in reverse of the other. So to begin with, let's suppose that the linear system is consistent. Remember that by definition, the term consistent means that we can find a solution to this. So that would imply that there's some vector x naught, which I'm going to write this way, such that A x naught is equal to B. So this is our solution that we know exists. If you go back to section 1.3, very far back to the beginning of the course, when we introduced matrix multiplication, we talked about lots of different ways of representing the product of two matrices. And in particular, if you're going to multiply a matrix to a column vector, some, in this case, n by 1 vector, we showed way back then that you could write that product this way. this is a linear combination of the column vectors in A. And the scalars that are used in that linear combination are exactly the entries in X naught. So what this is showing, using that result from way back in 1.3, is that our vector B, which is on the right side here, can be represented as a linear combination of the column vectors of A. But that, by definition, would put B in the column space of A, since the column space consists of all such linear combinations. So that actually proves the first direction that we wanted to prove. To go the other direction, let's suppose that B is in the column space of A. Now we want to show that there exists a solution to the linear system AX equals B. But considering what we did in the previous step, we can construct a solution from the scalars of a linear combination. So the fact that B is in the column space of A means that we can write B as a linear combination of the columns of A this way. Okay, so if those x1 through xn are the scalars that are used for that linear combination, we can put those scalars into a column vector and call that column vector x naught. And then we know that this left-hand side can be written as a x naught. Again, it's kind of like what we just did, but in reverse. That proves that the solution, or that the vector that we just constructed is a solution to the original system. And that proves the other direction. We have that ax equals b is consistent. Okay, so that's kind of an interesting characterization of the solutions to a linear system. All of the solutions have to live in the column space of our coefficient matrix. So here's an example. We want to determine whether B, this matrix here, is in the column space of this matrix here, and if so, we want to express B as a linear combination of those vectors. In light of the previous theorem, one way we can do this is show instead that AX equals B, where this is A and this is B, is a consistent system. In other words, we want to find a solution. And this is something you can do with Gauss-Jordan elimination. So I'm going to set up an augmented matrix for the system AX equals B. 1, 2, 0, 1, 4, let me just do B all in this column here, 4, 3, 5, 7, 0, 1, 2, 1, 1, 2, 1, 3, and 0, 1, 2, 2. Didn't leave myself quite enough space there, but that's all right. If we do Gauss-Jordan elimination on this matrix, then this ends up giving me the identity matrix on this side. And on the right-hand side, I'm going to get negative 26, 13, negative 7, and 4. Okay? So remember, this would tell me that this vector right here is a solution to the system AX equals B. So the fact that we found a solution means that the system AX equals B is consistent, which in light of the previous theorem would say that this vector B is in the column space of this matrix A. So that confirms that. Now what we need to do is find a way to express B as a linear combination of the vectors in A. Well, remember, this is my solution x naught right here, negative 26, 13, negative 7, 4. And in the previous theorem, when we proved it, we showed that these will end up being the scalars on the linear combination that we want. So I can write B as negative 26 times the first column vector in A, which is 1, 0, 1, 0. And then I can write 13 plus 13 times the second column vector in A, 2, 1, 2, 1. And then minus 7 times the third column vector, 0, 2, 1, 2. and then the fourth, plus 4 times the last column vector, 1, 1, 3, 2. And just to make sure that we did that correctly, it's worth going back on your own and checking to see that this linear combination, when you multiply in the scalars and add everything up, does in fact give us the original vector b. So I encourage you to check that on your own. Okay, next thing I want to talk about, another theorem. And this is a theorem that's a good characterization of solutions to linear systems. We've actually talked about this in the context of chapter 3, but this is another way of thinking of that theorem we talked about back then. It says, if x naught is any solution to ax equals b, and if S, this set here, is a basis for the null space of A, then every solution to the linear system ax equals b can be written in this form. Now, I want to point something, give some terminology to use here. X naught, we call this a particular solution. So it's some solution that was found ahead of time. X is called a general solution, meaning it characterizes all the solutions of ax equals b. Here, conversely, for all choices of C1 through Cn, this vector up here would be a solution of the system ax equals b. So to prove this, we're going to, there's two things to prove here. The first is to show these first couple of lines. So what I'm going to do is let x1 and x0 be solutions to this linear system. And then what I'm going to do is create a new vector, which I create by subtracting these two, x minus 1. I want to see what happens if I took that new vector, x1 minus x0, not x minus 1. If I took x1 minus x0 and plugged it into the left-hand side here, ax, that's going to look like this, a times x1 minus x0. Distribute the a in, I get ax1 minus ax0. We assumed that each of these x's, x1 and x0, were solutions to this system. So each of these should come out to b. Then I end up with b minus b, which equals 0. So what that shows is that this vector, x1 minus x0, is a solution to the homogeneous linear system ax equals 0, because I plugged it in and got a 0. What that means is that the vector x1 minus x0 is in the null space of A. Remember, the null space is the solution space for the homogeneous linear system ax equals 0. So we, in our the statement of our theorem up here, we said that this set S is a basis for that null space. So any vector in the null space of A can be written as a linear combination of these. In particular, I can take my vector x1 minus x0 and write it as a linear combination of those n vectors. Then if I were to take this equation here and add the x0 over, what I end up with is x1 equals x0 plus that linear combination. Now, I chose these two solutions to my linear system arbitrarily, so the x1 is really just any solution to this linear system. So if I just relabel that as x, then I have the first part of this theorem that I wanted to prove. The next part of this theorem, everything after the word conversely, is saying let's go back to this expression here, x0 plus this linear combination in those v's. This is saying that I can choose any numbers for the scalars in all of these values c, and no matter what I put in for those scalars, the result is always a solution to the original system. So in order to do that, we just say let C1 through Cn be any scalars at all. And then we define this new vector. I'm calling it x2 here, just to not confuse it with anything else I've used so far. Let x2 equal x0 plus that exact linear combination that we were talking about. And remember, these c's can be any real number now. I'm going to define a new vector v and just define it to be this linear combination, everything that comes after the x0. So c1 v1 plus everything through cn vn. Okay, well, v is a linear combination of the basis vectors for my null space. So that means that v is in my null space. And I could alternatively write this original definition for x2 in a more compact notation this way. Remember, everything after the x naught I was defining to be a v, or this vector v. So I could write x2 equals x naught plus v. So now, let's see what happens if I do a times x2. I want to see if I end up with a solution to my linear system. So if I do ax2, I can rewrite x2 the way that I defined it, x naught plus v. I can distribute a in, so I get ax naught plus av. Ax naught is going to equal b because x naught we assumed way up here was a solution to that linear system. Av is going to equal 0 because we showed here that v was in the null space of A. So that's what it means for a vector to be in the null space. It's a solution to the homogeneous linear system. B plus the 0 vector is b. So that shows me that x2 is a solution to the linear system ax equals b. And that concludes that proof because remember, x2 was chosen as this not linear combination, but x naught plus this linear combination where the c's could have been any real numbers whatsoever.